Thanks for being here. We're glad that we all made it on a rainy day. Today we're very happy to have Tolga Birdal. He comes from Imperial College London. Just arrived on a rainy day. We were also traveling with the trains from London. Apologies for the couple of minutes delay, but we are ready to go. So just very briefly, Tolga is going to tell us something about his work on topological complexity measures, on generalization bounds and neural networks. And so I leave the floor to Tolga, who is the best to tell us about all that.
Yeah, cool. Thank you so much. So in the recent times, I've developed this interest towards merging topology and deep learning, and some of the ideas actually come from neuroscience. Some of the ideas come from elsewhere, but we also started some other directions in that, and I think I'm gonna give you an overview of what all these are, hopefully in the next hour. Okay, so we are asking a fundamental question actually, and we are not the first ones. Many people ask that question. Well, we have this machinery, right? We feed it cats and dogs, and then at some point, surprisingly, I start to feed in some interesting examples, and it behaves very well, even without seeing them much, right? And so, what is this learning process? How is a neural network actually learning, and then how is it generalizing? In some recent works, people have argued that actually generalization is an extremely good proxy for measuring intelligence, because as you know, so I publish very often in computer vision conferences and journals, and what we do is we take a data set, we run our algorithms, we run our networks, and then we measure the accuracy on some with respect to some metric, whatever. And we claim that this neural architecture is actually intelligent, right, with respect to this metric. But this is a stupid way of saying this thing is actually intelligent. It just maximized one measure, right? So how is this actually happening, and how can we find these good measures? How can we speak about intelligence in general in these networks? And the claim is, so why this research direction started all of a sudden once again, right? I would say after 2017 or so. Because people have seen that, statistical learning theory was a big thing, right? It was going back to Vapnik and, all these great people, Puck learning and stuff. But people saw that, the typical claim that the networks are overfitting to data, and then they start memorizing the data. And this is why they are not going to perform well if you increase the parameters for an indefinite amount of time, right? But unfortunately, this is not the case in deep networks. So the training and testing is actually decreasing, together, almost together, as we add more and more parameters into the system. And this is not explained by the classical wisdom of learning theory. Right? So we discovered this, and we started to ask the question, why? Well, how can we develop a better learning theory for these things? And in fact, people have found out remarkable other properties that are, nowadays with the LLMs, people say that these are emergent properties. Some of them say they are not actually, right? But there are many, many properties. There are benign overfitting, double descent, and we see grokking coming along, and there is all these catapult effects, right? Slingshot mechanisms, and all those interesting mechanisms are just being born in the context of deep learning. Simply because big data regimes and big network regimes are different than the learning machines that we were used to. So in this work, I'm going to develop complexity measures for deep networks. These are important because they allow us to explain a lot of phenomena, primarily generalization. Because generalization, Puck learning has found out that a good proxy for generalization is network complexity, somehow the intrinsic complexity of the network. Right? People started to develop different theories for this. So there's information theory aspects, and then the heavy-tailed mechanisms in compression. These are kind of linked together. There's something called the singular learning theory. And mean field and chaos theories that come from physics and different disciplines, complexity science, network science as well. And these are theoretical. Let's say these green boxes are kind of theoretical parts. And then there are other works, and they say, well, I mean, I don't want to play in this theoretical regime and toy examples. I want to go to real world, explain real networks. I cannot really develop a theory immediately, but maybe I can do something empirical, which would, in the future lead to a good theory of deep networks. And these are also very valuable contributions in the field. So people looked at the topology of the computational graph or activations or the structure itself to quantify generalization. They also looked into intrinsic dimension. And intrinsic dimension is a very vague and general concept. People take it differently. They propose different intrinsic dimensions. We will also propose some dimensions in this work. Right? So mostly what I'm contributing to here is all these topology works on topology that benefited from algebraic topology to kind of explain neural networks. They were empirical so far, and we have kind of made the connection to we basically turned this blue box to a green box. Okay, so that is the most important thing we probably did, and I will explain how. And we see that the results are quite remarkable, actually. Okay, so what I'm going to explain is some kind of a new family of complexity measures that can theoretically bound generalization. And these complexity measures will be based on topology. So in general, the form looks like this. So there's on the left-hand side, there's some kind of a generalization error. We will usually speak of the worst case. And in the bound, you see that there are a couple of terms, but what we are essentially interested in is that topological complexity part, right? We will say that there is some, there is some kind of a quantity that you could compute through topology that's going to bound the generalization error. And then we are going to propose practical algorithms for computing this bound. This is very important. In mathematics, usually many bounds exist, and many of them are uncomputable. For example, Kolmogorov complexity would be one that is not computable, and that still bounds the generalization error, right? Would be a weak one and not practical. And then we conduct a lot of evaluations on this, and you are going to see a lot of correlations like that, right? So the y-axis in this graph is showing you the correlation of our measure with the generalization error. So, and all of these are our proposals. So you will see that, gradually we are getting better. Okay, well. So here is the setting. I'm going to assume the data space to be a product of the features and labels. I'm going to call this Z. And then I'm going to assume some kind of a training set S, right? That is kind of, that is in this data space Z. And then I'm going to assume a training algorithm, A. And this is going to output a trajectory. So I'm going to run my training algorithm from time 0 to time 1 or time t. And then as a result, I'm going to collect a set of weights, a lot of weights, right? WT at each iteration. And of course, this algorithm is going to have some kind of an algorithmic randomness. So which means there is, for example, if you are using SGD, there is a batch sampling, right? That is kind of random. Any randomness can work though. So I'm going to assume a loss function given the weights and the data, right? And then I will speak about true risk. So the true risk is an expectation over this loss, right? And this expectation is over all the samples, over all the things that you could possibly see in the whole world, right? It's not limited to S. It's not limited to training data. So that means that it's going to be uncomputable, right? That's going to be uncomputable because I cannot simply see everything in the world. So I will approximate this true risk, people also call population, with an empirical risk. And the empirical risk is going to be the one that is over the samples, right? And we hope that this empirical risk is close to the true risk, right? So just minimize this. Yeah. So what you see here this is the gap between the true risk, which is something I cannot compute, and the empirical risk, which is something I cannot compute. In fact, I compute this every day if I train a neural network. So on the left-hand side, you see that this gap between the two risks over the weights is actually the same thing if I were to take the algorithmic trajectories over time, okay, and computed the difference over that. So this is the same thing. So this is the previous result. It has been shown before. Okay, so looking at the, sup over the weights, at the end is somehow equal to looking at the trajectory. So now what is a trajectory? Let's take a look at it. So normally when you take a neural network and you start training it, you generate these individual, when you do a forward pass, you generate this data point, right, which is a neural network itself. Right? At each forward pass, actually at each backward pass, you update your parameters. Now you have a new neural network. It's a dysfunctional neural network, but it's still a neural network, right? So as you train, you are going to populate this space of neural network weights. If you were to think of all of the weights here as a big vector. So you take all these weights, put them in a bag, right? And that bag becomes 1 point in this data space, in this weight space. So this is some kind of a, if you want, Taken's embedding type of, dynamical systems, some kind of a embedding of a dynamical system, basically. You can think of it that way. Yeah, so as we train, we get these individual points in that space of weights. And of course, the gradients are a bit small, right? So at each time you make a small update. So you expect this trajectory to be a little continuous. Well, not a continuous one, of course, jumpy, but kind of, it's like a curve, right? It's not like a crazy thing. And so first that. Second, that trajectory has been generated by a training algorithm. So it means that if you were to, I don't know, if you were to take a d-dimensional space and just randomly sample points in it, randomly sample points in it, it's not going to be it's not going to be possible to generate this through training, through SGD based on the data you have, right? So basically, you cannot generate all trajectories. You can only generate the ones that obey some kind of a recurrence relation, because SGD is a recursive algorithm, right? So xt plus 1 equals f of xt, one way or the other, deterministic or stochastic. So that means eventually your trajectory is going to come from this iterated function system, which is going to give you a fractal. Okay. And it has been shown, I'm not going to go into the details, but the result of that training, it has to be a fractal in the space of weights. So that's interesting, because you can then start to speak about the properties of that fractal, simply because the algorithmic trajectory itself is also related to generalization, as we have seen in the previous slide. So for example, imagine the trajectory is three-dimensional now, or you make a projection into this 3D domain, and you can see how this curve can be, right? How this training can be, depending on different dimensions here. And this fractal dimension, when I say fractal dimension, I really mean some kind of an intrinsic dimension. And you could also embed these trajectories. So these are actual trajectories now. You can take a training trajectory and embed it in 2D using a multidimensional scaling, for example. And for that, you first need to compute a distance matrix. You could choose this different matrix to compute this distance, right? You could choose a Euclidean distance, or you could choose a distance that is induced by the data. So what I mean by that is you take your data, you feed it through your neural network, you get a loss. And then you get some other data and you feed, you get another loss. Or you take another neural network and you feed the same data and you get another loss, right? And you compute if the architectures are same. So during training, the architecture is fixed. If the architecture is fixed, you are going to be able to compute this, let's say, pseudometric, because it's a pseudometric. It's not a metric anymore. Yes.
So you could also, for the same data, have different hyperparameter.
Yeah. You could do all of that, right? But let's say right now we are training, so everything is kind of fixed, and let's assume our learning rate is also small enough, and kind of. I mean, you could change it, but let's assume for now hyperparameters are fixed, and I'm just training the network. And during training, I generate these different individual neural networks. Now I'm creating this distance matrix as the pairwise distance between all these neural networks. And the distance between two neural networks can be computed in many different ways. Euclidean distance of the weights is one example. And data-induced distance is another example, basically, because you compare the loss functions in the end. Right? And you can create your embedding of the trajectory like this. So you see that as I increase the learning rate a little bit from 10 to the minus 6 to 10 to the minus 4 in this example, I start to get these jittery trajectories. Right? So you already see that the character is a bit affected by the choices I make in hyperparameters, in this and that. You already know, for example, that in some, to a certain extent, increased learning rate is good for generalization, right? We like to use large learning rates as large as possible, of course. And yeah, here it's kind of reflected, the effect, right? And we will see how this is going to be important.
Both those figures were too long, and what was the distance metric for the top two fields? This rho S.
So the rho S is the data dependent metric. So it is the one that I have two neural networks. I feed the same data, and I compare the loss function in the end. That is, yes, and that is a distance metric. It's not a metric; it's a pseudo metric. So we say that this is this is rho S, and the other one is just the Euclidean distance between the weights. Okay, so this character of, so if I have a fractal in my hand, the first thing to do is you take this tool set from Mandelbrot and you try to apply it to this setting. And one of the most important properties of a fractal is its dimension. And in this case, there are multiple ways to measure this, Box dimension, Minkowski dimension. Here they tend to be equal in certain cases. For our cases, they are going to be equal. Hausdorff dimension, whatever. So in the previous work already, people have shown that the generalization gap that you see on the left-hand side is bounded by the fractal dimension of this training trajectory. Okay, so I have my trajectory. This gives me a fractal in space, and the dimension of that fractal is bounding the generalization error. To show this, they have made a lot of assumptions, unfortunately. And in the end, these assumptions made this uncomputable. I mean, there's a way to compute, but you need to make even further assumptions to compute that. So some of those are the assumption that SGD is a Feller process. So you basically take a continuous differential equation that is a stochastic differential equation that is driven by a Brownian motion or by a Levy motion, or a combination of those. So Feller processes are general family of processes that characterize this. And then you discretize this. You discretize it with different schemes like Euler-Maruyama, whatnot you can imagine, and you recover your training algorithm. So this is the assumption that your training algorithm has to come from this type of a continuous dynamics. And you see on the right-hand side, depending on here we assume like an alpha stable process, and depending on the heavy tail index of that process, you can see that the shape of the diffusion is changing. So the behavior is changing, right? And yeah, so that is one assumption. And the second assumption is that you start training your neural network, and you start to go around the local optimum, right? And you start to fluctuate there because there is some kind of a randomness coming from SGD, for example. And then the assumption is that around there, the gradient has to vanish. So this never holds, by the way, because you can never vanish the gradient completely. But this is an assumption that at the point of convergence, there's no gradient anymore. So we are at the local minimum. And the only remaining part from this previous differential equation that you see here is the diffusion, which means it is the noise. So it's kind of, it converged there, but it's just oscillating around it. So it's a special type of convergence. Okay, so if these assumptions, and many others, by the way, hold, people have shown that the dimension, the Hausdorff dimension of these weights are equal to the tail index of that Levy motion that we end up with. Okay. So the tail index is alpha in this case, and that's a theorem by Blumenthal and Getor from 1960 that alpha gives you the Hausdorff dimension. So you can apply this theorem, but to apply this theorem, it should only be a diffusive behavior. Okay. Good. So we want to get rid of these strange assumptions, and we have to look into some kind of a different mathematics to be able to do that. Okay, the question is here, so who knows what a persistent homology is? I just want to get to know the audience a bit. Okay, great. So no one. Or one, but it was a half raise of hands. Good.
Yes, persistent no.
Homology is persistent no. Okay, that's even more interesting. So you managed to escape from the from the persistence people and just remained in one. Okay. Okay, so we are going to analyze a given set. So imagine that this is like our weight space again, right? So training trajectory, whatever. But for the moment, I'm just going to say that this is a point cloud. Okay. And in this point cloud, we like to do, we like to extract some kind of topological features. I'm going to tell you why we want to extract topological features later, but let me give you this background on persistent homology. So I can do some interesting stuff. First of all, if I have a set like this, and if I want to create a topological space out of it, what I do is I choose a distance, and then a ball, right? There is this epsilon ball. Usually mathematicians love to write about this. And inside this ball, I see some points, right? And I can imagine this ball to be constructed on each point. And now these balls kind of intersect, and the points remain in some kind of, remain in the balls and sometimes not. So I'm just going to connect pairs of points that are no further apart than D. Okay. And if I do that, you see that there's a graph here. Okay. And inside the graph, there's a hole, but I don't know it yet. So this graph can capture connectivity, for example. It can tell you, which pairs of points are linked together, but it's not going to tell you anything about the holes or the voids or other higher order structures that are present. And topology allows you to do so. Okay. And that's important. So instead of the graph, we are going to build something called the simplicial complex. And what is that? So it is basically a complex of simplexes. And a simplex is the simplest element you can think in a given dimension. So if I have a 0 dimension, I just have a point. If I have 1 dimension, the simplest object would be this line segment between 2 points, or line. And then, as you go higher order, it becomes the 2 simplex, and 3 simplex becomes this like tetrahedron kind of structure, and so on and so forth. And if I put these together, I'm going to obtain an object as a complex of simplexes. Okay, so homology is going to count the components, the number of components, number of holes. Actually, I don't want to say holes, and voids, and so on. So a hole is something like that, right? You know that. And a void is a bit of a higher dimensional hole, if you want, or higher order hole that is, contained inside the simplex. And you can think of the higher order analogus of these things. Okay, and although that seems hard, it's actually computable via linear algebra. This is why persistent homology became very popular in recent times. Okay, so I talked about homology. I didn't talk about persistence at all. So the thing is, how do we choose this distance that I made a choice? I just made a choice. How do I do this? Right. So I say, okay, this looks like a good D, right? Maybe a little less, maybe a little high, right? So instead of that, right? So by the way, now I can build simplexes, right? Now I know that there could be triangles here. So I could actually connect them with edges and with triangles. But now, you know, that hole that I just created is completely dependent up to the choice of distance. Right? Now, instead of that, we consider all distances. So that's the persistence part. So each hole is going to appear at a particular value of that distance. Imagine that I pick it very small, there will be one hole in the data set that emerges. And as I thicken this hole is going to disappear, but maybe some other hole is going to pop up, right? So think of it like this. There's this distance, D1, and at D1, there's a hole. And if I pick the distance to be D2, and it's a bit larger than D1, this is going to disappear. Of course, the points are going to get connected, and I can build a simplex out of this, right? But there's no hole anymore. So the moment for these 4 points, this hole is born, is going to be called birth, and that the hole disappears is going to be called death. And persistence of a hole is actually the lifetime of this hole. Okay. So you can visualize this as a bar, okay, from the birth to death. Okay, it was born in D1 and died in D2. So the collection of all these bars on the entire data set is called a barcode, because there will be many such holes and many such shapes. Okay, so we could also build a persistence diagram. You get all these bars, right, and then you plot them in 2D. You just lift them basically. Okay, so instead of drawing AB as a bar, you just draw this as a point. Okay, and like that. So you will see if you do that, the large bars are further away from the diagonal, and the small bars are close to the diagonal. So that means, well, I mean, if you think about it, a long bar means that, you know, I was thickening my ball, I was enlarging the ball, and then I couldn't kill this hole, right? The hole survived for a long time, and that means it was actually a large hole. So it's a very significant hole. Whereas if the bar is very small, that means the hole, you know, it maybe it arises because of noise, maybe not, right? We don't know. So robust features, people believed to be the ones that have large bars. Okay. Unfortunately, this also was questioned, and recently it was changed. Right, people show that short intervals actually encode geometric information. Okay, like curvature, for example, you can recover curvature from this, which is a geometric quantity, not a topological quantity, although they are linked. Right, and long intervals represent the topological signal. So there is information contained, and intuitively, the rate at which this noisy things, the short bars basically decay, is linked to the dimension of the underlying object. So linked to the fractal dimension. Right? So that was shown by a sequence of works by Schweinhardt. Okay. Yeah. No. Okay, I don't know why this is not playing it. I somehow need to show this though. Let me see if I can. Okay, let me try to. Nope. Okay, I can't, but maybe I can write this on the board. Or maybe I have this equation somewhere later. Okay, so sorry, I'm just showing this because I cannot show the other one. So forget about the thing on the right. I'm going to define a quantity called an alpha-weighted lifetime sum. Right, that is going to be like all the intervals in the persistence diagram, right? So basically the lifetimes of all holes here summed up. So you take the absolute value of those, raise it to the power of alpha, and sum them up. Okay? That is called an alpha-weighted lifetime sum, and it was proposed long ago by graph theory people as an interesting quantity to study graphs. Okay. So then people came along and they defined this dimension. So already 2020, by the way. So these are also in mathematics community quite new. So they said, well, if I take the alpha weighted lifetime sum, okay, and if I, well, so if I look at all the alphas, okay, and the ones that are actually that make the alpha weighted lifetime sum bounded, okay, and there is a constant like that makes this bounded, right? And I do that over all subsets of the point cloud that I have, or of the weight space, basically. Okay, the infimum, so such of such alphas is going to be the dimension, the persistent homology dimension. Okay, so it's kind of like a search, if you want, right? You start to take all finite subsets of your set, and you are trying to ensure kind of like the smallest alpha that's going to make this quantity bounded. And that is going to be provably equal to a fractal dimension. Okay. Okay. So that was the bound that I showed you before. That was the fractal dimension generalization bound that appeared in early works that made a lot of assumptions. And from that, we transitioned to this. So basically, what we show is that this DMPH would be equal to DH for our setting of point clouds. Okay, and if I can show that equality, I could actually replace this DH by DMPH. And the reason why I do this is because this is a much more computationally friendly quantity, and it requires less assumptions. Okay, and therefore you can come up with an algorithm to compute this. It is like an intrinsic dimension computation or a non-integer dimension computation. You kind of you start to you sample your weight space. As you sample, you build your topological space, and then you compute these alpha weighted lifetime sums, and you kind of increase n. Okay, so increase the number of samples that you take at each iteration, and then you fit a line to the log of this. And that is the power law, basically. Okay, so if you do that, you are going to get a quantity, which is DMPH, okay, or pH dimension, that, and you can compute that on a neural network as you train. And then once this network is trained, you can go back to your data set and do all these tests that you have. So you do this, after training, which means you have not seen the test data up to the point where you computed the pH, right? That means you are predicting the generalization of a trained network without seeing the test data by this proxy that is pH dimension. Okay, and you see that this correlates quite well for different training algorithms and the different data sets and hyperparameters. So here we have different batch sizes. Previous ones we had different learning rates, and here we have different training algorithms as well. So now we don't have the assumption, the underlying assumption that we are optimizer or discretization dependent. That means we can apply this to many algorithms. Okay. And this is differentiable. So persistent homology is differentiable. And that means you can add this as a loss, like as a regularizer, just to promote generalization. So if you do that, you get a little bit of higher numbers in the test set. Okay. Okay, so people took this idea. Actually, mathematicians loved it also, because you can use topology to kind of speak something about neural networks now. But also there were other people. So some people, they actually did this data-dependent dimensions, and they have actually shown that there is a link to some kind of an information theory as well. I will show it in a couple of seconds. And then they also did the same trick of, so what we did was we took Hausdorff dimension or Minkowski dimension for that matter, which were equal to one another for our setting. And we showed that the persistence dimension is equal to those quantities too. So what people did, they took other type of dimensions, such as magnitude dimension, and also showed the equality of this magnitude dimension to pH dimension. And through that, they were able to replace the bound. And sometimes these quantities are better in terms of computation. So, they were happier this way. So what is this magnitude? It is like fractal computation again. So this entire thing is kind of similar. So you look at your data set from a very far distance, and then you start to zoom in. As you zoom in, you see emergent structures there, right? So something different comes up. The shape of the point cloud changes. And at every scale, you compute this quantity called magnitude, basically the pairwise distance between the points and stuff. Okay, I will show it in a second. And then you can draw a curve out of this. So let's just define. Let's just define the similarity basically of two things, I and j, so of 2 points, okay, as e to the minus some distance. And this could be Euclidean. Again, this could be data dependent, it doesn't matter. And then the magnitude is defined as like you take the inverse of that similarity matrix, and then you sum the elements. And you see that for the data set, that becomes a global descriptor actually. It is kind of a topological quantity also. So this is, that was defined. This is magnitude. And if you okay. Worked. Okay. If you were to, so let's say this zooming thing is parameterized in time by t, by a scale t. Okay, so you generate different copies of the data set basically, which are scaled differently. And at each time you compute this magnitude function. So you kind of compute the similarities between them and then take the inverse and blah, blah. And you can plot that in space, and you are going to get some kind of a curve. That is called the magnitude curve. Okay. And you can look at the magnitude curve, and you can do the fractal dimension-like computation again. So you take this delta to 0. So basically, this is kind of a classical dimension estimation technique. And you look at the log, and you fit a line to the log, just like we did before, right? And if you do that, that slope of the line is going to give you a dimension. And once again, you can plug it in the pipeline. Hey, training trajectories are there. From those, instead of computing the pH dimension, I'm going to compute the magnitude curve. I'm going to fit a line to this. And then I'm going to look at I'm going to quantify the dimension through that. Okay. So these are all nice. But as you see, there is always in the dimension computation some kind of a limit in case. Right? So we take some quantity to 0, some quantity to infinity, and things like that. This is not very practical in the settings where we operate, like everything is finite and discrete, right? So we are trying to propose something more practical. Well, the idea is, well, instead of looking at the dimension, let me just look at the quantities that I used to compute the dimension. Right? So can they bound generalization? If I can do that, I'm going to get rid of all the limiting cases as well, and all this gradient, stochastic differential equation assumptions, continuity assumptions also. So I can maybe work that, right? So we look at the alpha weighted lifetime sums, which is the core quantity for computing pH dimension, and the magnitude, which is the core quantity for computing magnitude dimension. Okay, and I also introduce another thing which will later be useful, the positive magnitude, which is just going to be some kind of a positive analogous of the magnitude. In fact, in the limiting case, they are equal. If you are not at the limit, they are not equal. Okay, I will only assume two things. First, the loss function we choose, so this pseudometric, is Lipschitz continuous and bounded. Okay, so that's it. And these are the only things that I require now. So we are able to trim down these assumptions quite a bit, because these are already certain assumptions that people admit in the community. They are not against these things usually. So bounded loss, and there are many practical loss functions, by the way, that can obey this. Okay, so that's fine. And I'm just gonna write this. Now, instead of the dimension itself, we can have a quantity of log of alpha weighted lifetime sum here. Okay, so the rest of the bound is a bit unimportant. Okay, so there is this type of let's say topological complexity here and some other terms here. And similarly, we can write the log of positive magnitude here. So these are not dimensions. You just take whatever you have and you compute that quantity, and you will see that this bounds. Okay. So the entire reason for that was we want to go practical, right? We want to be assumption free. We want to apply this to practical networks. And so we want to get rid of this toy regime, but we still want to keep the theory. That's the premise. And that's why what we did is we went on to now from CNNs or FCNs and stuff, we went on to transformers to evaluate this. And we went on to graph neural networks, which are, kind of two very different architectures. But if we can say something about those, it's going to be amazing. And we look at the worst case type of generalization error. Okay, so this accuracy test worst is basically you look at your accuracy for a while. You are training. You look at the accuracy for a little while, and then you take the one which is the worst. This plays better with the bound also. So that is well, we can stop here for a little bit. Well, okay. So I should also say we are reporting a lot of correlation coefficients. Okay, this should have been DS, but there is this psi learning rate and batch size that are the granulated candle coefficients corresponding to a certain hyperparameter. And there are the average of that, and then this is the candle coefficients that is directly correlated with the generalization. So here you see, well, this is the both positive quadrants, okay, in the batch size and in the learning rate. These are correlation coefficients, and we report for first of all a lot of topological quantities, the E of 1, which is the alpha weighted lifetime sum and positive magnitude, and MPH, which was the persistent homology dimension, so like a baseline. And then all these data sets and all these models. And you see that although the MPH doesn't perform very well in certain cases, right? So dimensions are a little bit limited in this case. Whatever we propose is behaving quite validly in this regime. So all these colors are actually our proposals, but here I am emphasizing more the first three. And across different algorithms now, because I don't care about the training algorithm actually. Essentially, in the discrete case, the only thing matters is that give me an update, any update. So I'm at this state of xt or wt, just take me to wt plus 1 with some kind of a, whatever iterative relationship. That's all I want. I don't have an assumption on that at all. So this part, is quite promising actually, I think. And this reflects to the data sets or to data sets and models. You can see in these tables that, like in general, if you look at the numbers, these are correlation numbers. I mean, you obtain without seeing the test data, you obtain in the transformers, right, and across various data sets, you obtain some kind of like 0.8, 0.7 kind of correlations with the test performance. I think this is remarkable that it's even achievable this way. And if you plot the actual correlations, so on the left-hand side there's the MPH. So that's an example that is discrediting the persistent homology a bit because that's from our second paper. But you see on the right-hand side that there's like the correlation is almost like a line, right? So that's I think quite promising. I was very happy to see these results. And then this generalizes to graph networks quite well. I'm not super good, but quite good, I would say. You see here on the left is alpha weighted lifetime sums. So it's our dimension and then positive magnitude. So for both cases. Right. And what next steps to take, right? What I haven't told you, and I was hiding it a little bit throughout the talk, is that yes, there is the topological complexity, but there is this other term that is tied to information theory, or some kind of an information theoretic quantity, essentially the mutual information between the data set and the weights. So that's a very hard thing to compute, okay? And we haven't done anything about it. Doesn't matter, I mean, well, for the sake of analysis, decreasing, sorry about the play in the slides. So decreasing the topological complexity still decreases generalization error, right? It still decreases the bound. And as long as these two correlate, we are fine. So correlation-wise, this term being super high doesn't really matter, right? You can have a very high term in the bound, but still, like this bound can be just 1 million. And if you reduce it to 900,000, right? If your generalization error decreasing together with that in tandem, you basically have correlation. That doesn't say anything about the tightness of this bound. And this is because of that term. Could be, right? And so we want to do something about this. Also, there are many other places where fractals emerge. So, for example, the decision boundary of neural networks have been identified to be fractals. I don't know if you know this work or not. But this is I think a remarkable discovery that really, like, you look at your decision boundary, it's like the coastline of Australia. Right? It's this fractal structure around it. So whenever you have such structures, you can actually analyze their dimension, and that can tell you something. Right? So even empirically, just take this empirically and look at it, could be something interesting. And we want to take this to the scale of language models. So I just want to show here in these data sets and networks we use, the number of parameters are about, let's say, 8 million maximum, which is still a remarkable number if you are doing theory, right? So we compute these things, we compute the distance matrix and all that, right? We can still deal with this number of parameters, but we cannot deal with billions currently. And one way to do this is, it could be just doing a projection, right? So do a projection into a 10 million dimensional space, which can be kind of okay if you can. Yeah, and we also want to look at other properties. We already started to look at adversarial robustness and grokking, from different perspectives, also related. And what I did was, whenever I create these topological spaces, I said that the entire network is composed of weights, and I can vectorize these weights and think of them as a point in a high dimensional space. Okay, but this completely disregards the architecture we have. So we can maybe look at the evolution of the architecture rather than evolution of the entire network as just one data point. Okay, so we are also working towards this other direction that merges topology and deep learning, which I'm not going to go into I'm not going to talk about it at all, but we are writing a book on that as well. So it's called TDL book. And that is for analyzing very complicated data sets that cannot be abstracted away by point clouds or graphs or CNNs. And this is a general framework to do that. I think it's a beautiful use of topology, and we are trying to, as a large group, we are trying to make this a thing, let's say. And yeah, I have a group at Imperial. I've been there for 2 years. And yeah, so we did a lot of good work with these people, I think, and we are doing. So yeah, they're just collaborations, and anything else, feel free to write me. And all these resources are online. So these are the 2 papers that I've talked about, actually.